Okay. Okay, we can start. So Ilker is going to continue on the fourth part of derived algebraic geometry, and he will be talking about higher spaces and symplectic structures.
Okay, thank you. So let me remind you very briefly what we discussed last time. Just some notations at least. So last time, actually, for for a given CDGA, remember we discussed the properties of the infinite category of commutative differential graded K algebras. So for such objects, we saw possible, relevant constructions. So if you remember, so we saw, for instance, I'm not going to give all details, but last time we saw, for instance, omega 1a. So this notation means this is like the modulo of a modulo of Kähler differentials, right? Analogous to one form. So if you are familiar with differential geometry. And what else? After that, we discuss what we call Derived algebra. Okay, Derived algebra, like exterior product of cotangent bundle, right? But the algebraic version. But this turns out to be a double complex. So therefore, we also have some d total, some total differential. You have horizontal and vertical differentials. What else we discuss? I guess we introduced the notion of derivations, and we discussed derivations on A. So we use this notation, der A. This is actually nothing but the vector fields, right? So these are like graded vector fields of each degree. So we have sum over all degrees. And this actually turns out to be exactly what you should expect, from vector fields. So this can be given like this. So we have home dg mod A from omega 1a to a. Okay, you should expect to see some identifications like that. And this space is exactly, just by definition, linear dual, right? So it's like linear dual of the cotangent bundle, right? Or the cotangent space turns out to be your tangent space, right? Similar idea. The analogous idea, and therefore for us these derivations turns out to be, actually we will use the following notation, TA. It turns out to be tangent complex, and this turns out to be our cotangent complex, so LA. But for some technical reasons, actually this identification not always true, but for nice CDGAs, this will be our construction. Okay, I don't know what else we did. Also, so these are some basic notations from last time. And another thing, we saw several informal definitions, right? It's like some informal definitions. So one of them is we use the notation spec A, right? But we need to be a little bit careful. This is not the usual prime spectrum of a ring, because this is now a CDGA. So therefore, we need to be a little bit careful. There are ways to define this thing formally. Actually, we are going to do this today. But these guys, formally called derived affine schemes. And actually, last time we defined such schemes, derived affine schemes, to be the opposite category of CDGAs. Okay. But actually, this is a kind of identification, so we skip these technical details. And so we just define the infinite category of derived affine schemes are just the opposite category of this category of CDGAs, infinity. And also, we discuss, for instance, if you have some object with a cover in this form, we call such things derived schemes, right? Derived schemes. So these are locally modeled on. So it's like you have some X, and also you have such affine cover. Okay? You have a topological space, and you have a cover covered by such affine spaces. Okay. But today, let's try to discuss these things more formally. So we are going to use sheaf-theoretical approaches. Okay, definitions. Let's say using sheaf-theoretic, I don't know, approaches. Oh, good. So let's see. So here is how we should define generalized spaces. So let me give you definition of generalized spaces. This is a kind of a diagram. It's a very popular diagram. If you look at any paper on derived algebraic geometry, you should expect to see a diagram like this. For instance, in classical theory, you can write down any scheme as a certain functor, right? So let me use this notation for the category of commutative K-algebras, no grading. Okay, so any scheme can be written as a functor, as a certain functor. So schemes can be seen as a functor like this. Okay, so this is what we call functor of point approach. Okay, functor of points approach. So we will discuss the details in a minute. So therefore, schemes are like certain functors satisfying some gluing conditions. So therefore, it turns out to be a particular sheaf. So by just playing source and target categories, for instance, this guy, you can consider the two category of groupoids. So remember the groupoids. So we discussed this before. Therefore, if you have kind of a groupoid valued sheaves, or like these functors, let me just say for simplicity, these are how we should define stacks. Okay, so stacks are groupoid valued sheaves actually, turns out to be. So the schemes are groupoid sets valued sheaves. And if you play this game, for instance, you can consider infinite groupoids. Okay, so this is how we define higher stacks. And also you can just you also have a natural embedding, because for any object in here can be seen as an object concentrated in degree 0, right? So there is some trivial grading with trivial differential, because don't forget, in this notation, A actually comes with some internal differential, AD. So we generally forget this D, but there is an internal differential. If the internal differential is always 0, you have this natural map here. So anyways, so these kind of functors will be called derived stacks. So this these are functors, but in particular they turn out to be a sheaf. Okay, so this is a sheaf of set, sheaf of groupoids, sheaf of infinite groupoids. Okay, so therefore there is also some kind of a gluing data. So it's a pre-sheaf particular functor plus gluing data, what we call descent condition. So we will come to that in a minute. So therefore these derived stacks for us, pre-sheaves, okay, pre-sheaves of infinite groupoids, okay, plus descent condition. Okay? Descent condition. So remember the definition of a sheaf. To pass from pre-sheaf to sheaf, you need to discuss how to glue things, you know, the identity axiom and gluing axiom. So therefore, we should. So we will see. I will give you a formal definition, but this should be our perspective. So let's talk a little bit more. For instance, what's happening on the right-hand side? Okay, what is the meaning? Okay. So the right-hand side. By Yoneda embedding, we will see. We will see. So I will show you what kind of map you should expect to see. So if you know all possible maps, so we will come to that, okay, in a minute. So let me just make a short comment here, and then we will proceed. Actually, what is happening here, right-hand side? Right-hand side, first of all, it's really about structure of a point. Structure, let's say, on the collection of points. For instance, if you consider the collection of a points of a scheme, they form a set. So points form a set, but for stack, points will form a groupoid. Okay, so this is the logic. And also plus, when you move, towards this direction, you will introduce more maps, right? Maps between maps, higher maps. So therefore, it's kind of so maps between maps. Okay, so therefore it's like infinite tower of equivalences. So maybe you want to decide two things are the same if there is a two morphisms between them, and then you just keep doing that. So it turns out to be, it will give you an infinite tower of equivalences. Infinite tower of equivalences. Okay, and the left hand side, I mean, if you look at carefully, so this A is just a generalization of C infinity M, right? The space of functions. So here, left-hand side is really about your space of functions. Okay, so you have just no grading here. For instance, f in A0. Okay, but here f in A. But now you have some kind of grading. So left-hand side is really about what kind of structure on your space of functions. Okay. Um, Good. So let's discuss this part in more detail. So if you have something like this, this is called sheaf of infinite groupoids, or sometimes we say homotopy. Okay? So derived stack is just a sheaf of infinite groupoids for us. So let's denote. So denote the category of or infinite category of such objects by just the. Let me use this notation. Okay. So let's analyze the objects. And for instance, let's take some x in this infinite category. Okay. So therefore, it's a functor, first of all. Okay. So you should expect to see something like this. So you have some functor. It maps A to XA. Okay. First of all, this is a functor. For each CDGA, it maps the infinite groupoid. But by Yoneda lemma, this turns out to be home, spec A, and X. Okay. So therefore, what does it mean? For any point, for instance, this is also valid in this perspective, also coming from, you can easily check the usual algebraic geometry. If you say, I just pick a point of a scheme, for instance, you should be able to find a CDGA such that this we call a point of X. Okay, so therefore this data always comes with, so you say, okay, there exists A such that P should be in XA. Okay, it's like when you have a manifold and you have a point of a manifold, this P, I mean, for this P, you can always find a chart. Okay, so it corresponds to this logic. But this basically tells you that any point can be seen as a map from spec A to X. Okay. So this is very nice. So actually P can be seen as a map. But actually this is also valid if you consider manifold theory. For any point comes with a chart. So therefore these are your affine neighborhoods, right? So for any points you have a chart. So this is like your chart definition. Okay? So you have an affine model, and for any point you will always find the affine space mapping to the original space. Okay? Therefore, once you know these maps, okay, once you know these maps, you can understand X itself. So the second observation. So actually this explains that map. So you can see the objects are either like this or like that. In that case, this maps to home space. So there is a input waiting here to X. Okay, like Yoneda embedding. So we also have some subcategory. So we say X is in the category of derived sheaves. I'm just saying category, but I mean infinite category in this D stack. Okay, when this happens, it means that such maps are embeddings. Okay, so such maps are embeddings. Okay, and actually, if you are lucky, if you are working with nice CDGAs, it turns out to be open embedding. Okay, this really behaves like a chart of a manifold. Define his notion with respect to the points approach. Yeah, yeah, yeah. I'm confused. So X at the beginning was a function, right? Derived X is a function. Yeah. But now you wrote home. So that's in the function category. Here, I mean, it's really like this. So you can see X as a topological space, and at the same time, you can define X by using this function of points approach. So these are two same things. I mean, same things using different approaches. Okay. Okay. So it's like you have a manifold. Okay. You have a manifold. You can describe this manifold by using all possible open maps in Rn towards M itself. Okay. These collections and satisfying descent condition give you the collection of chart perspective, but at the same time, M itself is a manifold. So we are just using two perspectives at the same time. But for us, it is, yeah, this is home in the infinite category of derived stacks. And these are like maps between two functors, if you want. Good, so this is one case. For instance, with this perspective, when X is affine, so let me write it down explicitly, this map. When X is affine, let's say X is spec B. Okay, X is spec B. It means this is a map like this. So it should be a map from CDGA to the infinite category of infinite groupoids. So it maps each A to map BA in CDGA. Okay. Good. Now you see the difference. Now we are considering maps from B, but here maps into over here, because when you apply the spec functor, it's a contravariant, so it changes the direction of maps. Okay. So something like this. So if you have an affine derived scheme, you should understand this map. If you have the global version of this thing, you should understand this kind of local model, okay, for a given derived stack. But for simplicity, we will use most of the time we will work with derived schemes. Okay, but we also have, I mean, this is the best possible case because of this nice open embedding property. This is not true in general. These are just arbitrary maps. But if you are working with derived schemes, at least you may have such kind of embedding picture. And we also have other nice stacks. I'm not going to give the formal definition, what we call derived affine stacks, derived Artin stacks. Okay, second best case. So if you check any paper, in most of the cases, if they prove something about derived stacks, most of the time they prove such things for derived Artin stacks. Okay? So these are reasonably nice, having nice behavior But this one is the best case, kind of. But if you want more general stacks, at least this is the second best thing you can work with. So if you check some papers, you will see that most of the results are valid for derived Artin stacks. Okay, but I'm not going to give you what kind of properties this Artin, let's say, provides. But instead, let me give you the following definition. Okay. In this definition, we will explicitly see this pre-sheaf behavior and descent condition at the same time, explicitly. So if you remember in the previous lectures, we discussed equivalent models of infinite categories, right? So the one of them, I guess, we're using simplicial sets, Kahn-complex approach, if you remember. So therefore, for instance, you can give the following definition as well. So derived stack is a pre-sheaf, okay, X from CDGA to simplicial sets, okay, simplicial sets. Instead of this infinite groupoid perspective, remember this enters the picture when you use topological categories, right, to specify a given infinity category. But also you can use a simplicial sets. Remember, an infinity category can be seen as a weak Kahn complex. So therefore, with this perspective, you can also give the definition like this. Let's say such that, so here is the first condition for each A, XA is a Kahn complex. Okay, it's a Kahn complex. And the second thing, for each open cover, so actually for each object and for each open cover of this object, okay. So the natural map, so you will have this natural map, XU. Okay, so the right-hand side, so you will consider all possible, maps like this. Okay, we discussed such diagrams before. You consider double intersections and triple intersections like this. In that case, I'm saying intersections, but these are like fiber products, And then triple version, IJK. And it goes like this. You have cosimplicial diagram. I guess this is the formal name. But of course, it goes like this. But you consider not limit, but homotopy limit of this thing. Okay? So it's, if you remember, this is like we also have a model structure. So if this map is a weak equivalence, then actually it corresponds to this gluing data. Okay? So remember the definition of a sheaf. Actually, you will have exactly the same definition, but it stops here. Because remember, to understand, for instance, a vector bundle, if you have, for instance, you have a section. If you have a local section on each cover, and you have, for instance, some kind of identification on the overlaps, and if you have a cocycle condition, this is enough data. So triple intersection, and you have higher coherence and higher cocycle conditions in that case, contrary to the usual case. So to encode this data, you consider this cosimplicial diagram, or simplicial diagram, so I don't remember the formal name, but if you consider the homotopy limit, you want this thing to be weak equivalence. Okay, so this is the most general way of writing this definition. But if you are familiar with this, some kind of technicalities, what you are doing is, if you have a model structure on the category of pre-sheaves, these guys turns out to be fibrant objects in that model structure. So this is some technical remarks. So derived stacks are, I mean, if you like this perspective, so they turns out to be fibrant objects in the model structure on this category. So pre-sheaves from CDGAs to simplicial sets. Okay. So if you like this perspective, stacks are just some kind of fibrant objects in the model structure on this category of pre-sheaves. Or if you want to write down this notion explicitly, it turns out to be particular pre-sheaves satisfying this condition too. So this is the formal definition, actually.
I have a question.
Mm-hmm.
But is open cover, you mean on CDGA?
Maybe I should.
Uh-huh.
Yeah, we have some Grothendieck topology.
How is it? It's a geometric thing, right? So we have
Mhm.
CDGA and
Mhm.
some.
Yeah, I mean, this is like this is also the opposite category of affine schemes. So for affine,
Cover, you mean there affine?
maybe I should say just maybe open might be a confusing. Let me just say affine cover. You have the usual Grothendieck topology sense. For any object, you have the collection of UIs and maps into that object satisfying certain properties. So Grothendieck topology, actually, in that sense. I mean, but this is just introducing the notion of a cover, right?
Why topos theory was
Yeah,
created?
yeah, I think so. Yeah, I don't know. Maybe I'm not that much familiar with that direction, but motivation maybe. I don't know. But let me just informally say, I don't know. Let's just, if you're confusing if I mean cover.
I don't know much about this theory. So this is called local homotopy theory, right? So in general, I guess the complex condition is it something related to good behavior of the spokes of the sheets or something?
Maybe the good behaviors on um, so I guess to make sense of the notion of composition, remember, we discuss infinite category in this perspective, to satisfy the existence of composing maps, at least remember the diagrams and inner horns like this, right? When you have something, I mean, when you have con condition, right, you can at least ensure the existence of this thing, but not uniquely. So that was the perspective.
Categorical angle, but
Yeah.
okay. So, but the diagram here is just in
Mhm.
simplicial set, right? And the
Yeah.
hole in my
Yeah.
hole in your taking full model structure, I guess.
Uh-huh.
Standard model structure.
Yeah.
Simplicial set.
Mhm.
So I guess at the end of the day, these are like bunch of spaces.
Sure.
And
Yeah.
you can define like sheaves of homotopy groups and so on.
Yeah. Of course.
Then,
Yeah. Sure.
and of course, you want to be able to keep track of these things.
Yeah.
And I guess having the CAM complex, I don't know from the
Mhm.
homotopy perspective, but you can at least define the homotopy groups of these.
Yeah, I think so. Yeah, of course, we will be interested in homotopy groups and everything.
But yeah, maybe it's like
Mhm. Uh, Good. So, any other comments?
I have another question. So if you
Mhm.
take not CTGA, but the most trivial case where we just have objects concentrated in degree zero,
Mhm.
and do this homotopy
These are just sets.
construction
Yeah.
then the simplicial sets are not.
Turns out to be just sets. So
Why are they forced to be sets?
I mean, not necessarily, of course. I mean, if you want schemes, so they are sets. If you just say higher, if you want higher, I just erase the picture. But
No, I just wanted to have an idea of
Mhm.
topology of the
Mhm.
domain category, right?
Mhm.
Because CDGA are more complicated, but if you take just schemes
Just
or something,
yeah.
concentrated degree zero, I can
Yeah,
see
sure.
the subcategory and I can
Sure.
take it,
Sure,
free
sure.
sheet and then put it back to the easier category with the easy topology. But
Yeah.
I can still do the homotopy stuff.
Yeah. Of course.
Does that make any sense to? Because the topology will be easier.
Yeah,
at least
could be.
for
Yeah.
more elementary than the CDGA.
Yeah, I think so. But I think the only thing is, so so remember when you have a, for instance, schemes versus derived schemes. So in that case, actually the points are the same essentially, right? So so therefore you may consider the truncation. This is maybe what you are doing. So you just consider, instead of the whole A, you consider A0, degree zero part. Then of course you can discuss such things. I don't know, maybe useful, maybe not. I don't know.
Yeah, I guess the reason I'm asking, I want to see somehow classifying spaces.
Yeah.
Somehow, and I guess you could do something with the, the Galois groups or something.
Could be. Yeah, maybe. I don't know. It's a good question, but yeah, I don't know. Okay, maybe let me briefly discuss, for instance, what about global functions? So how to define a global function on a derived stack, or how to define quasi-coherent sheaves, let's say vector bundle on a. So what should we understand? Because I'm not going to give you the whole technical details, but it might be very useful to understand what's happening. So what about, so the next question, global functions, or maybe quasi-coherent sheaves on derived stacks. Okay, so what should we understand? Right. So just recall, in usual algebraic geometry, right, in all ordinary algebraic geometry, so when we say, I mean, let's say X a scheme, okay, so a global function on a scheme, it basically tells you that, right? So you have a function on each, let's say, affine u, right? Compatible on the overlaps, okay? Compatible on overlaps. So this is what we should understand, basically. And so one way of formulating this is something like this. So you have this functor, okay? So O functor. So this left hand side, so this category is a category with object. So maybe I should write down. So this you see over X. So this is a category with objects being affine schemes. Okay, but you also have a mapping to X. Okay. So what it does, actually, you have some U, which is, let's say, spec R. It maps to R. Okay. So therefore, when we say something like this, for instance, we have some OX, and we have some F here. And what we want, usually, so we want something like this. So we just collection of pieces. So we just collection fi from each ui. Okay, we want something like this. But also, as you see, we want some compatibility condition. So what does it mean? Such that, well, this is what we want, and such that fi restricted to uij overlaps fj restricted to uij. Okay, in o ui intersection uj. Okay, so one way of writing this, actually we will come to this point. So one way of writing this, remember, using this i.e. what we want, we have this natural map actually, and the limit of this diagram OUI, and we also have two possible restriction maps, right? To the double intersection. Okay, limit of this thing. I mean, these two conditions turns out to be limit of this diagram. Remember how to define limit. This is the equalizer of this diagram. Okay, some object satisfying these properties. Okay, so global object satisfying these properties. So this is what we want essentially. I mean, here the limit is just equalizer of this diagram, right? No, I mean, equivalent way of saying this, existence of this limit and this isomorphism between these two things. This is the equivalent way of writing sheaf condition, actually, if you look at carefully. So this is what we should impose. Okay. So, long story short, so what we are doing here, the algebra of global function on x, okay, on x is actually to be the limit of such local pieces in this category. Okay? So therefore, with this motivation, we are just going to do exactly the same thing, but we want more coherence conditions, right? Like this. Okay? So, same idea, or with the same motivation. So here is the definition. If you have a derived stack instead of a usual scheme, the algebra of functions on x. Okay, so what we just use OX notation is just the limit of let me use R. R is CDGA and F in XR. Here, this R is nothing but O spec R. So what we are doing here, just replace everything with spec R, sorry, and the triple intersections and the higher intersections like that. Okay, we just consider the homotopy limit of this thing. So therefore, we impose this condition, but plus higher coherence conditions. Yeah, I mean Holland in that case. I mean, this is the limit in the category of CDGAs, infinite limit actually. Infinite. So we are just taking infinite limit in CDGAs. Okay. So therefore, when you write something like this, or
we get a CDGA when we take a bit.
yeah.
Okay, so there's a model structure there too.
Yeah, sure. Weak equivalences are quasi-isomorphisms. Yeah, yeah. I don't know. Only, I mean, there are nice models. I mean, for computation purposes, at least, I don't know. Instead of an infinite groupoid, maybe you use just groupoids. I mean, just consider stacks. There are nice models, at least. I mean, you can really write down, or you just consider stacks. So the target is not infinite groupoids, but just groupoids, two category of groupoids. So there is a nice way of writing this limit as a particular groupoid. Okay. But if you want the higher versions, it turns out to be very hard to keep track of, higher coherence conditions. But at least groupoid case, I at least know a nice model. So there is a homotopy theory of stacks paper. Yeah. Uh, uh-huh. Yeah. But in that case, so let me think. But we have, so now the source is like, yeah. Yeah, so let me think. Well, poets. Yeah, you're right. You're right. Maybe I should say, uh, so here, yeah, maybe we should be a little bit careful here. You're right. Uh, okay. So what's your suggestion? So this is an infinite limit in which case, in which sense? Infinite. Mhm. Yeah. Mhm. Yeah, yeah. Mhm. Yeah, at least for some working examples. Um, yeah, in this case, so therefore this is like infinite limit in infinite groupoids, you mean, right? Limit in infinite categories. So infinite limit in infinite categories of limit. Yeah. Uh-huh. Yeah. Mhm. Yeah, yeah. So this is like maybe infinite limit in the infinite category of categories. I mean, or the infinite categories, infinite groupoids. Maybe I should say infinite category of infinite groupoids. Uh huh. I think so. I think so. Yeah. Okay. Okay. So maybe let me briefly mention when we discuss quasi-coherent sheaves, for instance. So let me just say similarly, So you can write something like this. So if you want to understand the quasi-coherent sheaves on X, okay, and this turns out to be the limit R modules. So you now consider R modules. So R is like in CDGA and F in XR. So here, remember, so this, if you consider Q co-spec R, I mean the affine model, so this is like the R modules. Okay. So here, this one is CDGA. Now, in case of quasi-coherent sheaves, remember if you consider quasi-coherent sheaves on this affine schemes, right? It turns out to be just R modules. Right? So therefore, so what should we understand? For instance, a quasi-coherent sheaf F on X. So it will consist of the following data. So this is what we should understand. So the first data is for any R CDGA and any point, right? R point. So there exists an R module FF. Okay. First of all, if you say I have a quasi-coherent sheaf, if you consider just the vector bundles, but now instead of a vector spaces for each fiber, you have some R modules. Okay? If you want some informal way of saying things. So this is the first data, and the second data for any morphism, okay, something like this, and corresponding points. So we have this R point, and we also have S point, okay, such that x phi fr is fs. Remember, x is like a functor, so you should consider this thing as a functor acting on objects and acting of morphisms, okay? Such that there exists an isomorphism of S modules. So phi pullback f fr is like fs. Okay? For instance, the second data you should expect. And also you should expect to see the further coherence, I mean higher coherence conditions. But essentially, this is what we should expect. So in general, if you understand the behavior, we are just looking at this first level and second level data coming from these two levels, if you look at carefully. But you also have higher coherence conditions. So therefore, when we discuss derived schemes, at least if you want to understand global function, this is how you should think of global functions in terms of limit. Likewise, if you want to understand vector bundles, sheaves, or in particular quasi-coherent sheaves, I mean, you should understand such limit. Okay? I mean, this is how we define objects like that on a given derived stack. Okay, very similar to the usual algebraic geometry case when you have a scheme. But now you have higher coherences, and now somehow you need to ensure the existence of a limit. You need to use homotopy limit, or here like infinite limits.
X is an object.
Hmm?
If OX is an object, is OX an object of
Yeah, particularly. Okay, good. Actually, I mean, we don't have that much time, but at least let me mention the following. I mean, probably next time, I mean, we will discuss more in detail. Um, so for derived symplectic geometry, of course, we are going to use all of these ideas. But as we did over here for quasi-coherent sheaves or global functions, I mean, this is your structure sheaf, right? So now we will have something like this. Remember, we discussed theorem algebra, but for affine schemes, right? But now you can define this thing by using the same logic, limit in infinite categories, theorem A and A in CDGA. Okay? So therefore, for any derived stack, it is possible to define theorem algebra by using the same kind of limit approach. So you consider the diagrams like this. There are some theorem spec A, I, and then theorem spec A, IJ. So you just consider the fiber product. It goes like that. And when we say a global such thing, we mean the existence of this limit and this limit definition, actually. So for any derived stack. Okay. So therefore, this will lead to the notion of k shifted p forms. Okay. So therefore, shifted p forms on X globally. Okay. But for simplicity, we will discuss. I mean, for simplicity, let's focus on when X is spec A. Okay, affine case. So I'm going to define shifted p forms, shifted symplectic structures, only for such things, affine cases, but we know how to glue them, and or globally they can be defined like this. So probably next time we will discuss how to define shifted p forms on affine case, okay, on affine derived schemes. And also we will see some examples and some sample constructions. For instance, explicitly, we will see, for instance, -1 shifted symplectic structure. Okay, so what should we understand? And also we will discuss existence result, right? So do these objects exist? I mean, at all? Are they useful? So we will see some important results and applications. Yeah, so possibly next time we will discuss basics of derived symplectic geometry and applications. Okay, so maybe I should stop here.
Okay. Any questions?
Mm-hmm.
In this limit, how to use F? R is in CDGA in the limit, and there is a point.
Yeah, I mean, the role of F is something like this. So you should expect to see some local sections, and you want to glue these local sections like this, and you expect, for instance, I mean, the element of this thing is your F, right? So maybe if it's confusing, don't consider this one. But for any element, what I'm trying to tell you, for a local section satisfying some coherence condition on the overlap, and then you consider triple overlap and the higher overlaps, okay, all possible condition, and we say that they nicely glue together and you obtain a section. like this. So this is how your local section should like. So this is your F, but maybe it's like not just single R. So you have like UI, instead of UI, you have spec RI. Okay, so and you have many overlaps, and you want higher coherence condition, and therefore this is exactly what you should expect. So some Fi from when you have Ri here. So this is R is the limit running over R, if you wish. Okay? So just consider this one. This is the role of F actually. So you have local pieces, local sections, and some condition on the overlap, and then other conditions, co-cycle condition, when you consider the triple thing. So therefore you have a huge diagram like this, and you take the limit, and local sections are glued together to form a global one. Okay? So this is the role of F here, maybe implicitly. So I didn't write down this limit explicitly. Maybe this is the reason. It may look like.
So this thing is.
So here, this is the role actually. So for any R and F, so you have an R module.
It's a local R.
Yeah.
Then we do it.
Because for any R, so for any R, it gives you spec R, and spec R is your just some affine neighborhood, and there are many affine neighborhood like that. So and they behave nicely on the overlap.
So we glue all possible modules that we can local part of things.
Yeah, I mean, and they satisfy this property, and then you glue. Okay. If you consider the other way around, so you have this local information satisfying this one and that one and that one. They are all glued together to form a global one. And if you have a global one, it means that you have this data. Okay.
Is there an example?
Mm-hmm.
Calculation.
For which one? This one?
Yes.
I don't know, construction of any vector bundle by using, I mean, consider the global section. I don't know. I guess I don't have an explicit construction like this.
Like in the trivial
Maybe.
case, if you don't have any higher structure, you just have the theory of sheaves in algebraic geometry.
Yeah, I mean all of these things, sheaves, and if you want more, local free sheaves are just vector bundles.
Yeah, vector bundles are free versions,
locally
right?
free sheaves. Yeah.
But are we going to see an example of this lim computation for dr next time? Is that what you mean for
this one?
Yeah, just like doing an example and then defining example. I mean, like maybe seeing the construction and then maybe do you need the
we will
construction?
see an explicit P form on each affine scheme actually, but very roughly I will just so I'm not going to glue them actually. So we only see the local piece. I mean, because this part is kind of technical. I don't know. We only consider the P forms on affine patches actually.
Okay.
But explicitly, we will see some forms, how they look like. We will play with them, but so passing from local to global is like another process, but at least for us, because in general, I'm interested in the local structure theory. So, yeah.
Okay. Any other questions?
Okay.
If not, let's thank Ilker. Thank you.